And we're going to practice solving trig equations here. And like all equations, we want to start in this first example by isolating our variable. So we would subtract 5 from 3, and then we would divide by 2. So once we've got our trig ratio isolated, then we want to say where in our domain. Here we're looking for all the values in the first cycle around the unit circle. So where is the cotangent equal to -1? Well, that's exactly the same as the reciprocal. The reciprocal of -1 is still -1. So the places where the tangent and cotangent are -1 are the places where we've got 45-45 triangles, but one coordinate is positive and the other coordinate is negative. So x would be 3/4 pi in quadrant 2, or x would be 7/4 pi in quadrant 4. All right, the next problem asks us to use our n pi form where n represents any integer, so we want to add as many revolutions to our answer rather than just restricting the solutions to 0 to 2 pi. So we want to again isolate sine of x. So first we would move the 3 to the opposite side. We would divide by 4. And then we would take the square roots. Take the square roots plural. So I say that so you will not forget the plus minus sign. The square root of 4 is 2. And we recognize this is the long leg of a 30, 60, 90. So again, we're always thinking, you don't have to keep drawing these unit circles, but we're thinking of the places where the sign is either positive or negative, square root of 3 over 2. So I hope at first you think of a 30, 60, 90 triangle in quadrant 1, and then you realize that the other place where the sign is the same thing is straight across. And where is the sign equal to negative square root of 3 over 2? That would be right below these. So we end up with this butterfly kind of shape, and we come up with 4 different places in the unit circle. And now here is a place where we could write our answers a couple different ways here. Our first point is at pi over 4. And we could say, well, let's add all of the additional circles. Let's add 2n pi's to that. And then we could say the next one is at 3/4 pi. And we could add 2n pi to that. The next one is at 5/4 pi. So we could add 2n pi. And our last one is at 7/4 pi. And we could add 2n pi. And I just want you to be familiar with this method. In our textbook, we kind of stuck with this domain of 0 to 2 pi, but I want you to be able next year to translate to adding these unit circles. And there's one trick here that's worth discussing. Look at where pi over 4 and 5/4 pi land. Do you see that this is a diameter, this blue segment? These are exactly 1/2 of pi apart. So we could, instead of adding a complete revolution, we could add one semicircle. So we could, if you understand this idea, instead of adding entire circles, you could say, hey, why don't I just start at the first one and add semicircles, add 1n pi. So if you don't quite understand that, then stick with the green method of doing those two separately. But look at these two. If I switch colors, look at these two, 3/4 pi here and 7/4 pi. Do you see the same logic? That those happen to be exactly 1 pi apart. They are a semicircle apart from each other. So instead of doing them separately and adding an entire circle, we could start with the first one and just add semicircles. So there's sometimes some shortcuts here. So instead of writing 4 statements, we could get away with writing 2 statements. Now, don't worry about that for this year's final exam. I wanted you to be familiar with that method. On the final exam required problems, I think I'll stick with the 0 to 2 pi domain. Okay, so let's try it again here. So we want to solve, and it looks like a trinomial is equal to 0, so I suspect that we might be able to FOIL this. So I'm going to set up 2 binomials and find out if we can make this FOIL the same as any other quadratic. And I think if we put a -1 here and a +1 here, again, look what happens if you FOIL. The outside product is -2 cosine x's, and the inside is +1 cosine x. So the middle term works out the way we want it to. And now we've got 2 parentheses with the product of 0. So either the first parenthesis is equal to 0, or the second parenthesis is equal to 0 by the 0 product property. I'm going to subtract 1 to move it to the other side, and then I'm going to divide by that 2. And here I'm going to add 1 to the other side. And now I'm going to say where in the unit circle is the cosine equal to -1/2. The cosine is negative over here in quadrant 2 and in quadrant 3. So x could be 2/3 pi, or x could be 5/3 pi. And then where is the cosine equal to +1? That happens here. And now notice our restricted region is 0 to 2 pi. So which one is that? Is that 0 or is that 2 pi? I have to say it's both. So 0 and 2 pi are coterminal angles. They get us to the same place. So I think you'd have to have all 4 answers for this problem. All right, and let's try one more, letter D, and here we're asked to find all solutions again. So let me scroll a bit so I have some more room to work. And this time I see a binomial, so I'm not going to FOIL it. I would do that only for a trinomial. But when I look at this binomial, I see that it has a GCF of tangent x. So that would leave us with 3 tangent squared x minus 1. And again, if I have 2 globs with a product of 0, there's our 0 product property. Either the first parenthesis is 0 or the second parenthesis is 0. And you might be tempted to skip some steps. That would be perfectly fine. We're going to move the 1 to the other side. We're going to divide by 3. And then we're going to take the square roots, plural again. So 1 over the square root of 3, or if you prefer the rationalized form because you're more familiar with it, those are the same thing. So now let's think about our unit circle. When is tangent equal to 0? Tangent, by definition, is y over x. So y over x will equal 0 when the y coordinate is 0. So I think here we're going to get 0 and pi, and do we actually have to keep going and say 2 pi and 3 pi and 4 pi, or are we going to use n as an integer to show that that's going to have a pattern? So I think I would write this as x is equal to n pi. I could put 0 plus n pi if that you're not understanding why I'm doing that. 0 plus n pi. So we would get 0 first when n is 0, then we'd get 1 pi, then 2 pi, then 3 pi, then 4 pi. Would we also get the negative angles? Sure, because n represents all integers. So n pi for this answer. We still have this part to go here. Where is the tangent equal to 1 over the square root of 3? That's when we have short leg over long leg. So we've got 4 more places here. We want the vertical leg to be the short leg and the horizontal to be the long leg. So here we're going to get another butterfly shape. So we're going to get 4 more angles. And we could do them separately. We could say that's pi over 6 and 5 6 pi and 7 6 pi and 11 6 pi. And then we could add 2n pi to those. Or we could notice that these two are a semicircle apart from each other. They make a diameter. So we could combine these two together and get x is equal to pi over 6 plus n pi, because you're adding semicircles, one semicircle at a time. And notice that these two, if I switch colors here, these two in our picture are also a semicircle apart. So we could put them together and say, well, this is, the first one is 5 6 pi plus semicircles. Keep jumping. That's the same as saying now I'm going to add another semicircle and then another semicircle and so on. So we could write, we actually have 6 different places. We have these 2 points on the unit circle and these 4 points on the unit circle, but we can actually answer them with 3 combinations. And that's enough for this video.